Alright, so let's talk a little bit about tissue technique components that you're dealing with and using in lab. Right, this is the Robo TX controller we're using. Right, you see the USB input label here. You can also see where the external power supply comes in, the on-off switch. You can see where outputs and motors are connected. Then on the bottom you have counters or digital inputs, and those can only be digital in those counters. And then you see the 8 inputs for analog or digital inputs. As well on the bottom you can see a 9-volt out. That's if you need to run power directly to something. Also, notice that they've labeled the common ground on the inputs and the count. Alright, let's talk about inputs and closed loop. Alright, inputs provide feedback to the system. Systems that have feedback are considered closed loop. So no inputs means that no feedback, it's open loop control. Alright, so that means even if there's a body laying in that track on the top, then guess what? It's going to keep running. Right? Closed loop means there's some kind of feedback. In that bottom picture, what provides the feedback in that system? It's the 2 limit switches. Alright, so here's some photos of the digital inputs we have. You see the switch, that's a limit switch. It can be wired normally open or normally closed. Right? See then below that, the reed switch. Reed switches detect the presence of a magnetic field. The phototransistor, right, that says light, yes or no. It's important to know that that phototransistor has polarity. It does matter the orientation of the wires. Okay, and then the last one is the trail or the IR sensor. That actually is going to utilize 2 of your inputs. Okay, so phototransistors have polarity, guys. Alright, so how it's plugged in and connected to the controller matters. Alright, so this would be the phototransistor and this is your light. Alright, if the input on this one that's labeled I3 is connected and does not show a 1, if that light is on, you most likely have a polarity problem here. It's not that the phototransistor is broken. Right, so if you'll switch the wires on the phototransistor, you can do that either at the controller or on the phototransistor, either, not both, then you'll be able to fix that problem. That is almost always the problem, that on alignment with the light. Alright, so this is a program using the phototransistor. Right? You'll notice that anytime I'm using a light for a control system, the first thing I do in the program, the first thing, is turn that light on. If I'm using 2 lights, I turn both of those lights on. I want you to notice here that I did use that light as a motor only because I was not concerned about the number of inputs. Right? And then I give it a 1-second timer. And that's just like industry. Don't be fooled by that. You are going to have to get the pieces of your control system up before you begin to operate your system. Okay? So the next step in this program is the phototransistor, which is I1 in this program, is waiting to be broken. Okay, remember the normal output is a 1. So I have swapped the 1 and 0 branches. Until I break that light, I don't want this system to run. Okay, so this shows you where the phototransistor cannot see the light. See, I've turned my light on, but I1 is not checked. Okay, so if I'm just testing this in my interface, I can see I have some kind of problem. I always want to test my phototransistor once I have it hooked up and mounted. Right? In this one, the phototransistor can see the light. I have light is on in M1, you can see, and I1 is checked. It's a 1. Okay? So if you were in the other situation, you would need to check and reverse your polarity. Right? Okay. This is the wiring configuration for a trail sensor. Alright, I put the green to I1 ground, green for ground. Alright, blue was my I1 signal, yellow was my I2 signal. Alright, and then red I did to 9 volts power. Alright, so when I change the pull down menu on the interface test, I have to change it to the trail 10 volts. Okay, you're going to get a 0 when it's over black and a 1 when it's over white. Okay, let's watch this video. I'll show you a trail sensor being used. Okay, so now these are our analog inputs. We have the color sensor, the ultrasonic, a potentiometer, a photocell or a photoresistor, okay, and an NTC resistor. NTC, a negative change to temperature. It is a variable resistor that is sensitive to temperature. A potentiometer is a variable resistor. It changes as you turn the dial. Alright, photoresistor, a variable resistor that is sensitive to light. Okay, the ultrasonic sensor is sending out a sound wave and it counts to see how long until it receives the signal back. Alright, and the color sensor is also kind of a variable resistor similar to a photoresistor. Alright, okay, so the connections on the color sensor. We put the green to I1 ground, green for ground again, black is signal, and red's going to be power 9 volts. All right, be sure you change it to be a color 10 volt analog sensor on the input. Okay, this is a video of a color sensor being used as well. Alright, so that gave you an idea of a color sensor being used. Right, this is an ultrasonic. You can see the wiring here. Green ground, black signal, red 9 volts. Okay, be sure you change it to ultrasonic or you won't get any data back from that. Okay. Here are some outputs, okay, and let's talk about digital and analog. The outputs can be digital and analog as well. A motor, a lamp, and a buzzer are all analog. They are all analog. They are variable speed. That electromagnet, you can adjust that speed, but that electromagnet needs to be on or off. You need to use it full open or full close. So the electromagnet is digital. The motor, the lamp, and the buzzer are analog. You can tell as you adjust the speed, you'll be able to see adjustable speeds on the motor, the lamp, and adjustable brightness on the lamp. You'll also be able to hear the varying volume on the buzzer. Alright, this is an encoder motor. Okay, the encoder motor is an output and an input. Right? The output controls the motor. The input is for the counter. All right, so it actually ends up being wired to C, one of the C's, and the output. All right, but it gives you a very exact position.